All right, good morning. I'm Shadi. We are going to be talking about audio. Steven showed a very short demo of audio 2 nights ago. We had 2 talks that went over basics and again showed a little bit about audio, but I think the series of 3 talks we have planned for today shows things that either are easy one-liners, doable and fun and practical that can be done today with Mathematica. And a little goes beyond, shows the plan that we have, basically our to-do list, or at least a snippet to our to-do list for the next year and years to come. I would say the introduction of audio in version 11 was basically just a phase 0, as I call it, as it takes a lot of engineering work to get at least that audio GUI that you see that works seamlessly, plays streaming, in core, out of core, and all of those into the Wolfram Mathematica. And then really the meat is coming. A lot of processing is going to be coming, a lot of analysis is going to be coming, and some cool effects. Some of them are easy. We're going to be showing them now. But please give us feedback as the to-do list is evolving as we speak. So I'll start by some fun things, light things. Effects are going to be mostly cool. If you already have an audio piece that you want to add some kind of an effect to it, make it more fun, or actually make it more useful in sense of removing the noise or highlighting some specific frequency bands, or add a reverb to it so that it feels like you're playing it in some bigger auditorium or something like that. These are all kinds of effects that people typically like to apply to their audio signal. So let's just get started with some effects that are fairly easy to implement. Here I have a drum signal. The audio is not coming out. I don't hear it. Nope. Okay. Close enough. Can you make a tremolo effect of that as well? So what this tremolo effect is actually tries to modify the amplitude of the audio signal as you're playing it. So giving it, it sounds louder, less loud, and so forth. Okay. So basically, this is a very simple wave that I'm adding to the amplitudes of the audio signal. So as you listen to it, goes up again, comes down again. And it's fairly easy. I was emphasizing on this before yesterday, and I want to emphasize that again. With all the capabilities that comes with Mathematica, creating the kind of wave that you want to multiply to your signal to get a higher frequency and going up and down in loudness is fairly easy. And all we had to do as far as framework stuff is to give capability for simply multiplying your audio signal with another signal that is being generated with this piece of code, which is audio generation of a sine wave with the frequency and then shift it so that it doesn't go below 0, blah, blah, blah. So it's really, we're really trying to show all the capabilities of Mathematica that can help us create these kinds of effects and analyze the audio that comes next in the next talk. Another set of effects that people typically like to create are distortions and, moving the amplitude values up and down, taking them out of range and so forth. So if you look at the hyperbolic tangent, that's the plot. And if you apply that to an audio object, that's how it's going to sound. So very arbitrary. You can just play with all the numeric functions to see what makes, this is kind of an art. You can't say what's correct, what's incorrect. It's just what is fun. So similarly, this is a cosine wave, and just apply it to your audio object. You get a different effect out of that. And this is basically some people's profession. So another kinds of things that are very typical in the audio world are delays. A very simple delay, you basically have an audio signal. You decay it, repeat it, maybe add it to the original signal, maybe get rid of the original signal. Some of these very common ones, we made them actual audio functions in Mathematica so that you can actually pass the parameters that are very commonly useful, like the duration of the delay, the feedback factor or decay factor, how much you want to mix the input audio with the resulting audio, and so forth. So if you listen to the rule 30, which has been in Mathematica for a long time, and then add a delay effect to it. So it's kind of repeating with that 0.4 seconds of a delay time that has been specified. And by the way, useful to say that most of these arguments can be specified using the quantity specification that we have in Mathematica. So if you really care, if you have a very long audio, you want to specify the duration in minutes, hours, and so forth, these quantities really come in handy. And then the next thing I'm showing is kind of a chorus effect, which takes a bunch of delays and then adds them up together. So basically what I have is a table of audio delay of my original signal with some random delay value. And then I shift the pitch a little bit. Again, very typical for chorus effect. I'll talk about pitch shift later. And then compute the mean of all of those audio objects that were computed. So it just feels a bit richer when you do this. It sounds like this is not the very correct way, accurate way of creating a chorus effect, but the point behind chorus is that it feels like multiple people are playing that same piece, or multiple people, just like so many people singing the same piece rather than just one person. It just makes the audio a bit richer. Reverberation, as I said earlier, is a more sophisticated way of echoing your signal from the environment that you're in. And typically you get an impulse response of, say, just a bang, and then you get the response of that bang from the walls and the environment around it. And then that becomes what you convolve any other signal with it to get the effect of that same environment, that same room. So since I haven't played this yet,
right then, perfect timing.
This is just a male voice, and this is the reverb in some random environment of our choice.
Right then, perfect timing.
And then you can get an impulse response of any environment. We have, again, a couple of them in example data, like this St. Mary Church.
Right then, perfect timing.
And you see that the echo is coming there. All audio reverb is, well, there are various implementations of audio reverb, but basically how you can look at it is convolving a signal with the impulse response signal. And then just a couple of other cool effects that we are creating here. We are using some other signals, not necessarily impulse responses, like the clap. So basically multiple signals, and then convolving the signal with that. So kind of feels like you have multiple impulse responses over time. And yeah, again, this is there is nothing correct when we're talking about effects. It's just how cool or how fun it is. Again, this one, the church bell is triggering the reverberation effect. Or some water. It might be nice if you have the notebook, just play these audio themselves so that you get a better sense. Kind of feels like the audio on the rain. Okay, so this is just one other, again, kind of a random example using the delays and so forth that show the synthesis, the simulation of a vibrating string. So what we're doing here is that we get the frequency of the vibrating string that we want to simulate, specify a larger feedback, and start from a very small, very short noise. And all we do is that we are creating a delay, so many of them, add them together. And it really sounds like a vibrating signal. And then you add a couple of those different frequencies together. It sounds like strumming a chord basically on a guitar. And what we're doing to actually get the strumming effect here, just to show a little bit of the details, we are padding at the beginning so that it has the shift in time, so that they are basically played one after each other. So time stretching and pitch shifting, again, very common effects that people use. Will get the same male voice. The point of time stretching, you can basically think about, you want to stretch the duration or shrink the duration, and you can think about it a very simple way is just to extract the data, resample it, and put it back. But then in that case, you'll change the pitch. So proper time stretching is trying to change the duration.
Then. Perfect timing.
Without touching the pitch. So trying to preserve the pitch as much as possible, but change the duration. So this one is making it faster.
Right then. Perfect timing.
Or again, very convenient to have the choice of entering the some of these arguments as quantity. So you can say, I want the duration of the final output to be 4 seconds.
Right then. Perfect timing.
Frequency shifting and pitch shifting. What frequency shifting is doing is that it tries to shift, not tries. It actually what it does. It computes the short time. Does it do this? It is the short time. Okay. It actually tries to compute all the frequencies and shift them by a constant value. So as this picture is trying to show, if the signal has 2 fundamental frequencies, it moves them to F1 plus frequency and F2 plus frequency.
Right then. Perfect timing.
And then one thing that we want to do more of, but we haven't managed to put it in every single audio function that was introduced in version 11, are these kinds of time varying arguments. So here I said shift the frequency of my audio by 200 hertz, shift it up by 200 hertz. But I can have this argument be time varying. So for every time of my audio, I do a different shift.
Perfect timing.
So you can see that it goes up, it goes down, then it goes up, then it goes down.
Right then. Perfect timing.
Probably just a repeat. I don't know why I put that in there. So pitch shift, unlike frequency shift, multiplies the pitch, the frequencies that were detected by a specific factor. So again, the point
Right then. Perfect timing.
is to get different pitch, kind of mimic different person's voice.
Then. Perfect timing.
So here we are moving it by 2 semitones up or down. Compression and expansion, we don't have specific audio functions for them, but not that they're necessarily difficult. What they mean is that they're trying to make the whole, the overall, or if I can just show the platform, they're basically trying to reduce the dynamic range of the audio or increase it. So what they do in the case of compression, as you see in that plot, they're trying to attenuate the pieces of the audio that are loud, and so that they basically, it becomes more of a equally distributed based on the RMS amplitude or the loudness that we are computing. So what I'm doing here is that I'm creating a time series of, I created the amplitudes up there, and then I'm thresholding based on a specific threshold, which was that threshold up there in the plot, and then smoothing it a little bit. Then whenever I have values, amplitude values smaller than the given threshold, I would like to keep it as it is. Whenever it's higher than the threshold, I want to bring it down. And then I normalize it so that it's still at the same, almost the same loudness.
There are a lot of people my age that...
Sorry, let me play the original
There
one.
are a lot of people my age that need the bus in this area.
So as you see, there are some intervals of this audio signal that is quieter than the rest of it.
Need the bus in this area.
And if I plot it, you see that what has happened, these sections that are fairly damp are becoming closer in amplitude value to the rest of it. Since we are normalizing, it seems like we are basically expanding those silent pieces, but what we're doing is we're damping the louder pieces and then normalizing so that it comes back. As you see, there is no, the dynamic range of the audio overall during that duration of the signal is more uniform. So expansion is basically kind of the inverse of that. It's trying to find those quiet sections and diminish them, make them
There are a lot of people my
even
age
quieter.
that need the bus in this area.
And as you see here, these pieces in the original signal, we had some noise. They are becoming quieter, so that kind of reduces the noise that is in the background.
There are a lot of people my age that need the bus in this area.
it's difficult to compare. Probably would be better if you do it locally anyways. Creating an equalizer, we have a complete suite of signal processing capabilities in Mathematica. One thing that is newer in the pool of functions is a biquadratic filter model, which is basically giving us it's actually very common for creating these kinds of effects. If you look at the diagrams of how these effects are being created, how the transfer function models are being created, they're very often just a series and connections of some biquadratic filter models. So we have low shelf, high shelf, peaking, and so forth. Here I'm creating those and then connecting them serially together. And then here is a small GUI that shows for this periodic random noise, which basically almost has all the frequencies. We're trying to show how the equalizer can change some pieces of the frequencies. You basically would like to put favor for some of the frequencies in the signal and then diminish the rest of them. So that's that. And then if I change, say, the gain of the peaking frequency, reduce that, maybe enlarge that, you basically get a different response. That's basically the frequency response of the modified signal. And obviously, it was audible that the signal is different. Just to have a bit more fun with it, this was the drums that I played at the beginning. Let's change a few of them. Let's change a bit more. Harder to hear, but any of you that have probably worked in the field have had equalizers and know, these are typically these panels that you can shift the knobs up and down and so forth. More effects by modifying the short-time Fourier transform. So here I have a fairly noisy audio signal.
You will return safely to Earth.
Everyone knows that. And here's a spectrogram. So many effects are a lot easier, and in fact, a lot of the ones that I showed are being applied to the short-time Fourier transform of audio signals. This function that is in your builds, in the 11.01.11 builds actually, but we didn't manage to polish it enough to be released as a function, is getting a function that gets applied to every single value. This is showing the magnitude of the short-time Fourier transform, but you, in fact, if you call the spectrogram array, you get a bunch of complex numbers. And this function gets applied to every single complex function of that spectrogram array, and then we compute the inverse of that to get the modified. Well, this one is using a white noise and tries to, okay, so one thing, again, these are no promises this function, if gets released, is gonna have the same structure. But the plan is that this function, this arbitrary function that can be specified, gets two arguments. One of them is the value that you get back for every single response in the short-time Fourier transform, and the other one could be the time. And so here we're just showing a simple example of using. And as you see, I started from just 5 seconds of a white noise, but based on the time that I'm specifying, and I don't recall what was the third argument. Frequency, yes, time and frequency. So we get the value, time, and frequency. So and there are just a ton of things that can happen with these kinds of functions. More of it is going to be coming in the next version. And then this is basically the last slide before we move on to more serious stuff. We were thinking, we were looking at this short-time Fourier transform of an audio signal. And there are some community posts and blogs and marketing examples about converting an image to an audio or an audio to an image and blah, blah, blah. And then I thought we have all of these image processing capabilities, of course. Why wouldn't I think about it? And then what we decided to do is to come up with, we have an image transformation function that gets an arbitrary function, moves every x, y coordinate of the image to a new x prime, y prime coordinate in the image. So all we're doing here is that we are computing the spectrogram, and I wish we had matrix transform as well as the image transform. Maybe we should have it, but we're sticking the real and imaginary part of this spectrogram array into an image and actually calling image transformation on it, then do the inverse to get a new audio object. So let me run all of this notebook or slide because some of them take long. And then I can basically go through them one at a time. So this basically gradient image is just showing what kind of a transformation we are applying to every one of these spectrogram arrays. So this first one is basically taking every xy coordinate and push it to an xy to the power of 1.2. And this is the kind of a transformation you see. That's the spectrogram. And which audio I'm using? The noisy talk, the one that the lady was speaking. So let me actually play that once again. Now I can't. Okay, hopefully you remember because the other cells that I run are already evaluating.
A lot of people my age that need the bus in this area.
Again, sorry, no science behind any of these. These are just fun things we came up with yesterday. This one is reversing the xy coordinate as you see. So basically puts the time domain over frequency and kind of sounds like a creak. Oh. Yeah, it was kind of empty at the beginning because there are not so many responses on the top of the frequency space. This one is mosaicing the image, so basically gets every chunk, every like rectangle, computes the mean, and then replaces all of the pixel values with that. So did the same thing to the short time Fourier response. Still could understand what the lady was saying. This is a kind of a rain effect. Feels like XYs are coming down, or in the Y direction we are coming down. Again, same effect applied to the spectrogram. Okay, the fisheye effect failed, but actually what is failing here? Let's see. We got an audio object back. I don't think it has worked. Maybe I changed something last minute. Oh, okay. Well, let me run them again. They were working before. All right. I still have practically 4 minutes. I can steal a bit from Carlo as well, who's coming next. But this is basically the last talk. And as I said, we made these 3 talks in a row. This was the sweet, easy one. Carlo is going to show us the meat of the analysis and synthesis, which has a lot of use, in various domains of research and development. And in fact, some digital composers may like or moving towards doing these kind of programmatic synthesis. And Carlo himself is a musician, or I can say. So anyways, very exciting talks. Really would like to encourage you to don't leave for another hour. Thank you.